A real nice application of integration is the ability to find arc length. Now, we know how to find the distances between 2 points in a plane. So if I had as example xy axes, and I have this point and this point, which has coordinates x1, y1, and x2, y2, I can find the distance between these. We know how to do it. It's just a distance formula. If I think of this as being delta x and this as being delta y, then the distance between these 2 points, I'm going to call it s this time rather than d for distance. I'm going to say s is equal to the square root of delta x squared plus delta y squared, where delta x is obviously the same thing as simply x2 minus x1, and delta y is the same as y2 minus y1. So this is the standard distance formula from way back in algebra. Back in algebra, you referred to it as d for distance. Only here, we in calculus, we commonly use s for arc length. Don't ask me why it's an s. It just is. So finding 2 points is easy, but what if I have a situation where I don't have 2 points? What I have is some curve, maybe like this. And I want to figure out how long this curve is. Well, if I break this up into pieces, maybe let's just say a piece like this, a piece like that, a piece like this. Each of these will have a delta x. I'm going to say this is delta x1, and this is delta y1. This one's going to have, well, I didn't draw that very good, but this would be delta x2, and over here would be delta y2. And of course, this piece is going to have delta x3 and delta y3. Now, I could actually calculate the distance between this point and this point with the distance formula, this point and this point with the distance formula, and finally this point and this point with the distance formula. Add them up, and it's going to give me an approximation for what this curve length actually is. Now, each piece would be based on, well, this would be like the first piece. The next piece, this would be, rather than x1 and x2, be x2 and x3, the difference between these two, and so forth. So I can represent this as the sum I equals 1 to n. In this case, n would be 3 because I broke up into 3 pieces of the square root of delta xi squared plus delta yi squared. This is just adding up to 3. With a little bit of algebra, I can write it in this form. And let me show you the algebra real quick. See, delta xi squared plus delta yi squared. This is the square root. If I factor out a delta xi squared, it will come out as simply a delta xi. And behind, I have the square root of this becomes a 1. Plus, there are no delta x's here, so if I factor out delta xi squared, I have to have it in the denominator. So I'll have delta yi squared divided by delta xi squared. All that's under the radical, and I factor this guy out, so here's my delta xi is setting right there. That's where this actually came from. Now, clearly, this approximation will get better if I let n go to infinity. And in here, kind of implicit here, is the fact that all these delta x's are the same. So delta xi, they're all going to be the same width. Otherwise, I have to be talking about letting the norm of the partition go to 0. So if I simply let n go to infinity, then delta xi goes to 0, and that gives me an infinite number of these little segments. So rather than on a curve like this, rather than having like big pieces that I'm adding up, I start getting a bunch of little teeny pieces, and I get an infinite number of these little pieces, and that's what this is representing. So the infinite number of these little line segments will give me the true arc length that I'm looking for. A sufficient condition for an arc length to be rectifiable, a rectifiable simply means that it has finite length, on a f of a to b f of b. Just notation wise, let's make sure that we know what we're talking about here. Say here's a to b, and let's just say I have a curve that looks something like this. I'm trying to figure out how long this is. Well, this has coordinates, x coordinates a, y coordinate is f of a. This has coordinate b, the y coordinate is f of b. So I'm going from this point to this point. The sufficient condition is that the first derivative of f be continuous on a to b. So if whatever this function is, if the first derivative is continuous, and that's a sufficient condition so that we know that the arc length is rectifiable, it's of finite length. We're not going to end up with an infinite arc length. Now, since the first derivative, that's f prime, is continuous, the mean value theorem is going to guarantee the existence of some value ci in the ith interval, such that the difference between these two can be represented as the first derivative evaluated at ci, some value that's in this interval, times xi minus 1. This is just a repeat of the mean value theorem. Now, if you're not familiar with it, that looks foreign, then go ahead and look in your book and find the mean value theorem as a quick review. This then implies that delta yi over delta xi is equal to f prime of ci, which is another form of the slope. To see where that comes from, you can see that f of xi minus f of xi minus 1, this is delta yi. So this is equal to f prime of ci times x minus, xi minus xi minus 1. Well, this is delta xi. So if I divide both sides by delta xi, that gives me delta yi over delta xi equals f prime of ci. Again, this is based on the mean value theorem. And this is right here. That's where that actually comes from. So what this is all implying then is that if the arc length is approximated, say S is approximated by, and we said this a moment ago, the sum I equals 1 to n of the square root of 1 plus delta yi over delta xi times delta xi, and this, I'm sorry, that should be squared, and this is the same as f prime of ci, then I can say that S is approximated by the sum I equals 1 to n of the square root of 1 plus f prime of ci times delta xi. Well, these c's are just various values of x. So if I take the limit as n goes to infinity of the sum I equals 1 to n of the square root of 1 plus, I forgot to square this. Sorry, I keep forgetting to square that quantity. Right there, that needs to be squared. 1 plus f prime of ci squared delta xi. These ci's are actually just different values of x. This is a definition of an integral. This is the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. So this we can use to find an arc length for some curve from a to b. This a to b is this a to b. So providing the first derivative is continuous, all we need to do is find the first derivative of the function, 1 plus the first derivative squared to square root. If we can integrate this, then I can figure out how long this thing is. So by definition, let f have a continuous first derivative, that's what I've been talking about, on some interval from a to b. The length of the curve from a f of a to b f of b is, and this is exactly what I just got done writing on the previous page. And if we have a curve that's defined as a function of y, the definition is similar. Rather than the a to b, typically we may say c to d to denote that we're integrating with respect to y. And this would be g prime of y dy. But the exact same idea goes if we're integrating with respect to y. So this is the formula or the approach that we will use to calculate arc lengths.